Hello everyone, my name is Gianluca and I will introduce you to our paper CROCODILE, Causality Aids Robustness via Contrastive Disentangled Learning. So this work talks about bias in medical imaging applications and how we have developed a new framework to force the model to avoid spurious correlations that arise due to biases and shifts. In this regard, causality matters, and we studied the problem by analyzing colliders and confounders. So from a causal viewpoint, we can represent the problem of classifying medical images, I, coming from different hospital sites or domains, D, for the presence of some medical conditions, Y. We can thus identify a subset of features that we name causal features that truly determine the outcome, and a subset of spurious features that are not causally related to the outcome, but can be, let's say, better predictors due to domain shifts. And similarly, we can predict the domain D from which the images come. So here we leverage the intervention tool from causal theory, and as you can see from the hammer, we applied this intervention intervening on the causal features, that thus breaking the backdoor path that would spuriously predict the outcome via the spurious instead of the causal features. And this way the model learns a better and more generalizable mechanism. This is the overview of our dual branched system we named CROCODILE, but do not be intimidated. I will break it down to different parts. So the first stage is feature extraction, where we have two branches, Y and D, one for the disease or condition prediction, and the other for the domain or dataset prediction. By leveraging over 500,000 images coming from 4 popular chest X-ray datasets, we trained these convolutional backbone feature extractors, and then the feature learning block, which enhances the features according to, for example, a CS attention, so channel and spatial attention. And the input here is composed of the medical image sample, so X, and both the disease label and the domain label. Then comes the disentanglement and contrastive learning block, where we modified the transformer network to yield not only A, so the attention scores, but also its complementary set, 1 minus A, so that to identify the causal and the spurious parts of the input. And we enforce the correctness of the causal ones through cross entropy loss, and we enforce the not utility, let's say, of the spurious ones, thanks to a KL divergence loss through a uniform distribution over all possible classes. Next, we implemented some loss terms concerning the contrastive learning scheme. And for example, at the batch level, we can see that we can enforce, for example, consistency between samples of the same disease or samples coming from the same domain. And on the other side, we can enforce, let's say, the separation of samples coming, having different diseases or coming from different domains. So the following step is the backdoor adjustment. So we implement it as a latent causal intervention. So in the latent space, as you can see, we stratify the spurious set of features and compose them with the causal ones. So borrowing from others, we conceive this backdoor adjusted set of features, and we push their prediction to be invariant and stable across stratifications. The next contribution of this work is named relational scorer, and which is a learnable regression layer, let's say, that learns when two kinds of representations should or should not be aligned. For instance, we want the causal features that truly determine, let's say, the disease, Y, to be somehow related to what is not useful for predicting the domain, D, and vice versa. The final last contribution of our work is a novel way to inject prior medical knowledge into the model learning. We thus design a graph of chest X-ray findings and conditions according to the literature and create the so-called causality map, summarizing the probability of co-occurrence among those labels. For instance, if you find pneumothorax, then it is highly probable that you also see atelectasis, so the lung collapse. So during learning, we use the causal features of the disease branch to compute such causality map and force it to be close to the ground truth one. Coming to the results, in the end, we can see that the double branch nature of the system and the contrastive loss terms and the injection of prior knowledge led our model to perform best on the out of distribution data, leading to the lowest drop in performance, passing from in distribution to out of distribution data. So this concludes my presentation. So thank you and see you soon.